Good morning, everyone. We'll continue today with our lectures, and today we will look at electric potential energy and uniform electric field and due to point charges. So let's start with the uniform electric field, where basically we have a uniform electric field generated by parallel plates, and then we have released a charge inside this field. In this case, if no other forces, external forces applied on this charge, then the charge is going to see a force exerted by this electric field and will apply that force in a way such that the work done by this field is a positive work, and the electric potential energy of that charge will tend to decrease. So how is this happening? We've seen from earlier lectures that the difference delta U, which is the electric potential energy for the final state minus the electric potential energy for the initial state, equals to minus W. W is the work done by the field in this case, and we know that the work is the dot product of the force with the displacement vector. Now, in case the field is the only force applied on this charge, then this charge is going to go toward decreasing its electric potential energy, which means it will go in the same direction of the displacement vector, which means that they will overlap and the dot product would be positive because we've we've seen earlier that the the result of a dot product between two vectors is the magnitude of the first one times the magnitude of the second one times cosine theta, which is the angle between those two vectors. So in this case, the displacement vector and the force vector will overlap, and the angle theta would be zero, and that's why the whole cosine would be one. And in this case, I have the work done as QE delta R. QE is the force times the delta R, and we have said that the force is in the same direction as the displacement vector. So in this case, the difference delta U, which is the difference between the electric potential energy of the final minus the initial, equals to minus, here I have minus. Then in this case, this, as I said, delta U is U2 minus U1. U2 is the final, U1 is the initial, equals to minus Q E delta R. And as you can see, U2 is less than U1, which means that the final state of the electric potential energy is smaller than the initial. And this is basically proves what we have just said, that if there are no external forces applied on a charge in the existence of an electric field, then this charge will tend to go in the direction such that its electric potential energy decreases. So let's look at this example. In this example, we have a uniform electric field generated by this infinite plate, where we have an electron that is here at 1 meter from that plate. Then the electric field is a uniform electric field with a value of 150 Newton per Coulomb. We need to calculate the electric potential energy relative to the plate. So in this case, we will be using the electric potential energy of the plate as our reference. And in this case, this is going to be U2. U2 will be 0. And this is the location of U1. In this case, I want to calculate the electric potential energy at position 1 with respect to position 2. And in this case, we will say that delta U equals to minus W, which means U2 minus U1 equals to minus. Now, this is an electron. The displacement vector is this one. This is delta R. The force applied by the field is opposite to the electric field. So the force, this is the Fe. And in this case, the work done would be negative. Why? Because the force applied by the electric field is pointing upward. However, the displacement vector is pointing downward. I'm calculating it with respect to the plate. So in this case, I have here minus, the work is negative. Then in this case, U2 is 0 minus U1 equals to W, which is Q E D. Delta R here is this distance D. In this case, U1 would be minus Q as the magnitude 1.602, 10 to the power minus 19 times 150 times 1. And in this case, U1 equals to minus 2.4 10 to the power minus 17 joules. So U1 is a negative potential, electric potential energy with respect to the plate, which means if this electron has to go downward, it will gain electric potential energy, right? So it will gain the electric potential energy because right now it is at U1 is negative minus 2.4 with respect to what? With respect to the electric potential energy of the plate. And this makes sense because this is an electron, and if this electron has to go downward, it will have to go due to an external force. And this is the external force that caused this electron to go in the opposite direction that it wants to go, which means it will go toward increasing its electric potential energy. If it reaches the bottom plate, it will gain 2.4, 10 to the power minus 17. But right now it is at minus 2.4 minus 17 with respect to what? With respect to the to the plate. So this is the direction. If it's released, if it's released with no external forces, it will go in the positive direction of y. It will go this way. However, due to the external force, it will go downward. And if it goes downward, it will gain 2.4 10 to the power minus 17 joules. If we release it, it will go upward. It will go in the positive direction of y because it will go toward decreasing its electric potential energy. If we release it with no external forces, but if there is an external force that is pushing this electron toward the plate, it will gain electric potential energy. Okay, so far we have seen what's going to happen if I put a charge in a uniform electric field, which means the electric field is uniform everywhere within the region that we are evaluating this electric potential energy. However, what happens if The electric field is not uniform. This happens if I have two charges. In this case, let's assume I have this Q1 that is positive and Q2 that is positive as well. So what's going to happen to the Q2 if I assume Q1 is fixed and I released Q2? We know that there is a force that is repulsive applied on the Q2, pushing it away because both are from the same type of charge. Both are positive, and in this case, this force is given by Coulomb's law as this. So at this location, if we assume that this is R1, then I have here FE1. Now, what's going to happen if this charge moves to this location? Then the force is going to change. It will not be FE1 anymore. It will be FE2, and the distance will also change and becomes R2. What does this mean? This means that this force is not going to be a constant force. The force is not uniform. Why? Because the electric field is not uniform that is generated by Q1. It varies. Varies by how? Varies by inverse proportional to the square distance in between. So in this case, what do we do if we want to calculate the work? Does the work expression that we have seen earlier in uniform electric field, if you recall, as F delta R, if they are going in the same direction, can we use this to calculate the work for the case of non-uniform electric field, or which is going to result into a non-uniform force? Of course, no, we cannot use this expression anymore because this expression assumes the electric force to be uniform at every single point within that region. Now we have a force that is changing with the distance. So in this case, what do? We have to integrate. Integration is basically as if we are discretizing this path into this infinitesimal pieces and calculate or accumulate all of them to find the work. So in this case, let's look at this example to understand what does an integration mean. If we have now, we're talking about those two charges, Q1 that is fixed and Q2 that is allowed to move. Now let's see what's going to happen if this Q2 takes this path from point A to point B. Let's talk about this path for the time being. What's going to happen is if we are to apply, because now the electric field is non-uniform, so the electric field at this point is different than this point, different than this point, different than this point, and different than this point along the whole path. So in this case, I cannot say that the value of the if the force is uniform, I have to use the integration. So if I am to use the integration, how do I solve it? Okay, let's assume we have this Q1 and this Q2. Both are positive. One of them is fixed. This one is fixed. This one is allowed to move. Now the distance here between them is RA. Call this one RA. And once this one moves, due to the applied force, so let me draw the force. So this is red. It's going to exert a force, repulsive force in this direction, right? Then this charge, let me call this one F1. Now this charge is going to move to this location. Now this is location, I'm calling this one A, and I'm calling this one B, and that's why if this is RA, then from here to here is RB. Now there will be a force due to the Q1, but this force is going to be less than F1. Let me put the force here. I'll call this one F2. So the force is going to become smaller and smaller once this Q2 moves from this location to that location. Along this path, there was a work that has been done. However, because the force is not uniform, I have to do the integration. So how do I calculate this work? So let's see. So W from A to B equals to, we said the integration from RA to RB for the force dot. Now this path, this path, if I am to integrate along this path, I have to pick my differential element here. Now, because this path is a vector, and I'm integrating along this vector, which is this delta r, then I will need to pick an infinitesimal piece that I am calling, because I am on the x-axis, I will be calling dx. However, this is a part of a vector, then in this case, this is going to be also a vector along the x-axis, and this is usually called dl vector. So this infinitesimal element here is a vector, which is the dl, and this dl equals to a dx along the x-axis dot this dl, and then now we can say that this w is integration from RA to RB for the force, which is K Q1 Q2 divided by x squared. This is my variable now along the x-axis. I hat. Now the unit vector for this force is I hat dot this dl, which is the x I hat. Now here I have two vectors, but both of them are on the same direction, same axis, and we know that the dot product for 2I hat is 1, dot product of 2j hat is 1, 2k hat is also 1, because the magnitude of the first is 1 times the magnitude of the second. So let me do this one here. The magnitude of the first is 1 times magnitude of the second, 1, cosine theta. Here the angle is 0, and this makes the cosine equals to 1, and this the answer is 1. So my work here, W, is K go outside, constant, Q1 constant, Q2 constant, RA to RB for dx over x squared, then W as K Q1 Q2 minus 1 over x RA to RB, and now this the work is KQ1 Q2 substitute and rearrange becomes 1 over RA minus 1 over RB. So this is the work for going through that path. Go back to here. This is path 1. So that's the work that has been done through going through path 1. Now regarding for path 2, so we said that this is, we have here A, B, C, and D. So this is the work that we get for going from point A to point B. Now, if I want to evaluate the total work that the field is doing on this charge, field coming from Q1, if this charge goes all the way through path 1 and then come through this path, BC, and then CD, and then DA. How much would be the total work? So we have calculated path number 1, A to B. Now for path number 2, B to C, we can see that the force everywhere along this path is perpendicular to that path, and that's why the work is 0 due to the dot product between the force and the differential element of the of this path. So along path BC, which is path number 2, we have a 0 work, and also the distance did not change. The distance was always fixed RB. So we have a 0 work for path number 4 that goes also from here to here. We have also a 0 work because of the force being perpendicular on the differential length for that path. So I ended up with path number 1, which is the work that I derived earlier. And for path number 3, which is going from C to D, if you do the derivation, you will find that the work is the same in magnitude. However, the sign is negative, which basically, if you now add all those works together, work 1, work 2, work 3, and work 4, you will get 0, which means that the total work done by this field to take this charge Q2 all the way during this path and come back to the same initial location will result into a 0 work. Now, in order to derive the electric potential energy expression for two charges, then we'll take this work that we have derived, and knowing that delta U equals to minus W, then I can rearrange such that this delta U becomes, this is U2 minus U1 equals to minus W if you multiply by -1, I get U1 minus U2 equals to W. Now this U1 is basically at point A. This U2 is at point B. So I now have this relationship that is UA minus UB equals to the work that I have derived earlier. Now, if I take the second point for RB to be at the infinity, which basically is going to give me a reference of UB being 0, then I can now say that the electric potential energy equals to KQ1 Q2 divided by R, whereas my reference of RB going to infinity would be 0. So this is going to give me now the electric potential energy between two charges at one location. Now, this electric potential energy that I have derived for between two pointed charges that are at a distance of r, if I take this distance also to infinity, this is going to result into my electric potential energy between those two charges to be 0. Same thing for the electric field. If you recall, K Q 1 over R squared. If I take this R to infinity, then the electric field at the infinity would also be 0. Same thing for the forces. If I take this distance between those two charges to infinity, then the force would be also 0. So if I am to calculate the electric potential energy for a charge, then in this case I have to include all the other charges in the calculation. For example, if I am to calculate the electric potential energy for a test charge that is Q naught, then in this case, if this is my Q naught and I have Q1, Q2, Q3, in this case I have to take the summation of all the electric potential energy due to those charges, which means that U tot would be electric potential energy due to U1 naught and also U2 naught plus U3 naught. And I have to calculate the electric potential energy for all those pairs and then add them to get the electric potential energy for the test charge Q naught. So the relationship is U total for this Q naught equals to the sigma, which is the summation of the electric potential energy between this tested charge and all the charges that are close to this charge. Now, in case I want to calculate the system of the point charges, not the electric potential energy for one charge with respect to the others, no, I'm calculating the electric potential energy for the whole system. In this case, I have to take the pairs only for one time, which means I have to avoid the self iterations, which are those ones, KQ1, Q1, based on this based on this expression. I have then to avoid the self iterations, which are the R22, R33, and only take the pairs only once, which means I have to avoid the Q2, Q1 if I am taking the Q1, Q2. Also, if I'm taking the Q1, Q3, I have to avoid the Q3, Q1, which means no double counting for those pairs and no self iterations. This would be the system of point charges. Now let's take this example. In this example, we have an equilateral triangle where we have a negative charge here, positive charge here, and a positive charge here that are equal. We need to calculate, assuming that the electric potential energy is zero when the point charge is at infinity. This is, as I said, the reference. Then I need to calculate what is the electric potential energy of the charge minus Q. Electric potential energy for this charge, I have to include the electric potential energy between minus Q and plus Q and minus Q and plus Q as well, which basically is going to result into the double of the electric potential energy because the distances are the same and the value of the charges are the same. That's why for U minus Q, it will be 2 times minus Q, Q small divided by D. So this resulted into 2 times this value. For the UQ positive, either this one or that one, it is the same. I will have to include, this. Let's take this one. Let's take this one, the one here. Then I will have to include the positive Q with a negative, this one, which basically is going to give me minus KQQ over D, and then the positive and the positive, which is KQ squared over D. Now, what is the potential energy of the system? It's now different. For the system, we have to take the pairs once. So what do we have? How many pairs do we have? I have one, two, three pairs. So in this case, it will be minus KQQ, this one, will be minus KQQ, and it will be KQ squared over D. So you add them together, and this will be the electric potential energy of the system.